This is another u sub for an indefinite integral, so that means our answer is going to have a plus c, so keep that in mind. So how do I go about this? Well, I'm going to do u sub, so cup, so c is what I care about, so I care about what my u is, what my du is, what my dx is, and what my x is going to be. So how do I pick du? I'm sorry, how do I pick u, excuse me. So usually what I tell you to do is like, take a look at this integral and ask yourself, what is the trickiest thing or the trickiest looking thing? And you're like, okay, well this. And so I tell you pick what's on the inside. But recently when it comes to trig, I've been telling you to rewrite it as tangent of x over 5 to the 9th power. And then I tell you to think about it that way, like, okay, what's the trickiest part about this integral? This, and then pick whatever's on the inside. But that's usually when there's like just x, right? But you've never seen something like this where it's like x over 5. You might be like, okay, well, let me make my ux over 5 since there is something in the inside. But think about it. If you've noticed the pattern with u sub, the whole thing is when you substitute dx and put it in terms of u, whatever's in the denominator is going to cancel out with the other thing. So you want something related to secant in the denominator. And if you pick x over 5 as your u, everything after that, everything that's related, is not going to have anything to do with secant. So your dx is not going to have anything to do with secant, so nothing is going to cancel out there. So you want something that's going to have to do with secant. And so most likely another trig function is going to have some sort of relation to secant more than like an x over 5, because like derivative integral of x over 5, like they're just numbers, right? And variables, they're nothing to do with secant. So that's my reasoning for why I like to, even if there's stuff inside, I still rewrite it like this, and I use that same rationality. I'm like, okay, what's the trickiest part about this problem? Well, this, and so I'm going to do what's on the inside as my u, so tangent of x over 5. So it's going to be my u, and so then my derivative of that, if you don't remember, I got this table off of Cole's World of Mathematics on YouTube. So the pattern is secant, secant, cosecant, cosecant, and then tangent, cotangent, and this is negative, and then the arrows point inwards. So then the whole idea is if you want the derivative of tangent, it's going to be secant squared, because secant, secant. So that's going to be secant squared of x over 5. And then because this is something on the inside, you have to do chain rule, so times the derivative of what's on the inside, that's going to be 1 over 5. But if you want the work, if you have x over 5, that's quotient rule. So f prime of g minus f g prime over g squared. It's really like f prime of x, g of x, f of x, g prime of x, but I don't write it like that, even though that's how I first understood it. It's really just that this is like the top function, this is the bottom function, or f of g. I just read it this way because it's faster. So then I like to do f, g, f prime, g prime. Okay, so what's my f? It's always the top, so that's x. My bottom is 5. So remember, this is just like f of x, g of x, and so on. So then derivative of f, so f prime is 1. Derivative of this is just 0, it's a constant. And so then you put it all together here. So f prime, that's going to be 1 times g, which is 5, minus f, which is x, times g prime, which is 0. So this cancels out to be 0, this cancels out to be 5. And then over g squared is 5 squared, that's 25. So this is 5 over 25, which is 1 over 5. So that's the work there for you. And then this is times dx, it's always times whatever's here. And so then for dx, you just solve for dx. So that's going to be, we're going to have to multiply by 5 to get rid of that. So 5 du, and then divide by whatever's next to dx. So secant squared, x over 5. Okay, and then I don't solve for x until I go to the next step, and then if things don't cancel out, then I solve for x. But when there's trig, here's my hack. When there's trig, I never solve for x. Never. It usually always just works out. And if it doesn't, then you're in Calc 2, because it's always going to work out in Calc 1. But if it doesn't, you're in Calc 2, and you have other strategies. Okay? So then u is put everything in terms of u. So that doesn't include the bounds because there are no bounds. So we're good with there. And so this, I made my u. So u to the 9th, and then secant squared x over 5. I know this isn't in terms of u, but remember the whole pattern is that whatever is your dx, which is 5 du, secant squared x over 5 is going to contain something that's going to cancel out with this. So in this case, these cancel out. Isn't that beautiful? So get rid of that. That's supposed to be a du. And then we have a nice little thing here. We can move the constant outside because everything's being multiplied together. And so now we have a beautiful integral. Take the antiderivative. So you're adding plus 1, that becomes 10, divided by that same thing, 10. You can pull out the 1 over 10 because this is really 1 times u to the 9 over 10. So pull out the 1 over 10, u to the 10. This is all being multiplied by 5, and we're doing a plus c because it's an indefinite integral. And you can distribute the 5 in, so that becomes 5 over 10, which is just 1 over 2. And then the p in cup, right, is you're plugging u back in. So because you don't have specific u's, because it's not a definite integral, you're going to plug in like the general u. So that's going to be, oops, what am I doing? 1/2 tangent of x over 5, probably just do that, to the 10th plus c, or you could just write it as this. All right, that's your answer.